week 2 Thursday asynchronous lecture. So today we're going to go to 2 examples of centric buckling, and then we're going to talk about eccentric buckling, the theory of eccentric buckling. So let's look at the example number 1 on centric buckling. So what you can see over here is we have aluminum column of length L and a rectangular cross section, and has a fixed end at B. So at B is what we classify as a fixed end. Okay, as I mentioned before, fixed M, when it's fixed M, moment is not equal to 0. Okay, and it supports a centric load at point A. So we have a centric load over here. 2 smooth and rounded fixed plates restrain NA from moving in one of the vertical planes. Okay, so in terms of movement at point A, right? Later on we'll draw at different planes. How does the fixturing, or how does the condition change when you look at different planes? Okay, so but allow it to move in the other. So in one of the vertical planes of the symmetry of the column. Okay, so moving in one of the, and the other one is allowed to move in the other plane. I will explain this later on when we draw. Okay. Determine the AB ratio of the 2 sides of the cross section corresponding to the most efficient design against buckling. Okay, so we will later describe what do they mean by efficient design. So design the most efficient section of the column, knowing that the length L is equal to 20 meters, Young's modulus 10.1 times 10 to the power 6 psi. Load is 5 kilo pounds, and there's a factor of safety of 2.5. Okay. So we are going to deal with A first. Okay, we're going to do part A. So part A, it requires us to determine the ratio of A to B such that the 2 sides of the cross section correspond to the most efficient design against buckling. Okay, what do they mean by that? Right. So in order to explain what's going on over there, we have to look at the structure in 2 different planes. Okay, so we know that is our transformation. This is our X, this is our Y, and this is a Z. So what we are going to do is we are going to look at the plane. We're going to look at XY plane. Okay, so we're going to look at XY plane. And we're going to focus what is going on at point A. Okay, so I'm going to sketch out XY plane. So we are viewing at XY plane. So viewing XY plane, so this is, if I were to draw the transformation, this is our Y. This is our X. Okay, and then we have our rotation about Z. Okay, so we're going to sketch this out. Okay, so it looks like this. Right, so one end is built in. So this is where our point B is. And point A, you have 2 restrictions. Okay, so this is our point A. And then we have a load that's coming down P. Okay, this is our load P. Right. So how this will buckle? So we know at point B is fixed. So we know that moment in the z-axis is not equal to 0. Whereas at the top it can rotate. Okay, so moment about z. Okay, so moment about z is equal to 0. Okay, so when that's the case, sorry, it's not 0, but for this case, it's also pinned. Okay, if we were to look at over here, it's restricting its motion in the x direction. So x is equal to 0. Okay, so when you look at a structure like this, right, how it will buckle, I will go into our buckling figure now, like what we have for. Okay, so what we have, if we have a structure very similar to this, okay, very similar to this, and I will copy and I'll paste over here, and I do beg your pardon, the moment is in fact equal to 0, okay, because there's no restricting moment over here. So m is also equal to 0, right? So for this case, when we view it at the xy plane, it's very similar to what we have over here. Okay, so we can say that one end is fixed. So this is our fixed end. And on the other side is our pinned end. And why we call it pinned? Because moment is equal to what? Moment is equal to 0. So for this case, with reference to the figure that I've attached in, the equivalent length is equal to 0.7 L. Okay, that is our 0.7 L. So the next thing is what we're going to do is we're going to find out what is our IZZ. Okay, and why is it on the IZZ, right? Why is it on the ZZ? Is because how the bending will occur. Okay, why we use our ZZ axis. So if now we have, I'm going to sketch out our centroid. Okay, so if this is our centroid, the structure will deform. Okay, based on this plane, on the XY plane, it will deform this way. Okay, you deform. Oh, sorry, the built-in have to consider the built-in. When there's a built-in, the slope is equal to 0, so it has to be a straight line first, and then you do this. Okay, so this is the deformation. So looking at the deformation, the curvature, right? The curvature of the deformation, which is I'm highlighting in yellow now, is the same curvature as RZ. So when that's the case, we have to determine, okay, we have to determine okay, we have to determine IZZ. Okay, determine, I think I always we have to use IZZ. Okay, we have to use IZZ. So by looking at the transformation over there, IZZ, so if we were to draw the cross section, so I'm going to draw the cross section view now. So this is our Y and this is our Z. Okay, so I'm going to sketch out our cross section view. Okay, so this is wing for the top and the axis of interest. And this is our axis of interest now, which is our ZZ axis. So this is our ZZ axis. So we know, right, from here, we know that this is our width. And over here, this is our depth. And we know the values. This is our geometry over here. This is our B. And the geometry over here, this is our A. Okay, so we know we have to use IZZ. Right, so the next one, but before I go on, what we are trying to do over here, okay, what we're trying to do over here, let me correct this term over here. I want to rewrite this. Okay, so this, in fact, I'll call it LE on the XY plane is equal to 0.7 L. Okay, so looking at like how I'm approaching this problem, why are we doing this for? Okay, so we always know the slender ratio okay will determine when buckling will occur. Okay, so what we have just done is we have analyzed the structure in the XY plane. So what we want to do is this. Okay, we want to make sure that the slenderness ratio, so LE at our XY plane divide by RZ. Okay, RZ is the radius of gyration about the Z-axis. That is why, so if we look at over here, we know that, note that IZZ is equal to ARZ squared. So we know that RZ is equal to square root of IZZ over A. Okay, so that's how we define it. So we have to ensure that we have the optimum design. We have to ensure that the slenderness ratio in the XY plane, okay, will be equal to the slenderness ratio. So the next plane we're going to look at is the XZ plane. Okay, XZ plane over now have to determine over R over RY. Okay, wait, let me have a look. So we are looking at the XZ plane RY. Yep. Okay, so to satisfy the optimum dimension, okay, criteria, right? So we now, for now, we know, okay, for now, along the XY plane, right, the equivalent length is equal to what? 0.7. So then another thing that that changes over here is if we were to determine IZZ, okay, IZZ, and IZZ is equal to, so is equal to B A cube over 12. Okay, so we know that IZZ it is now equal to B A cube over 12. Right. So over here, from here, we can also determine our RZ square. Okay, we can determine our RZ square. Right. So RZ squared, I'm not going to square root yet. So RZ squared will be equal to IZZ, which is BA cube over 12, right? And then divide by area, which is B and A. So RZ cube is equal to A squared over 12. Okay, so we know that this is equal to A squared over 12. Okay. So that is where we analyze our buckling on the XY plane. Okay, we come up with our R squared is equal to A over 12, and if we put it to RZ, okay, if I were to put it to RZ, this will be equal to A over square root 12. Okay, So we have satisfied, so we have finished analyzing the slenderness ratio for LE XY over RZ. Next, we're going to find along the exact plane. So now